This video is sponsored by Flexispot.
My life revolves around motorcycle engines. I currently have 6 of them, which seems like a lot, especially considering I only own 2 motorcycles. I have owned a number of motorcycles, but also cars with motorcycle engines, including the world's fastest car powered by a naturally aspirated 1-liter. Motorcycle engines are amazing. The power density you can get out of them is more than most multi-million-dollar supercars. They are basically full-blown race car engines for just a few $1,000s. And I am in the middle of disassembling one, so I thought this would be a good time to talk about why they are so amazing and why they make so much power. Before we talk about why motorcycle engines make a lot of power, we have to talk about how engines make power. Combustion requires fuel and oxygen. The fuel you get from the gas station, the oxygen you get from the air around you. A piston engine is an air pump. It pulls in fresh air from the world around it, mixes that with fuel, and then ignites it in a combustion chamber. This combustion creates a high pressure that pushes down on the piston. The combustion is doing work by moving the piston. The faster the engine spins, the more work you can do in a given time. Work per unit time is power. So there are 2 ways to make more power: more combustions per minute or more work per combustion. More combustions per minute is just revolutions per minute, or RPM. Just spin the engine faster. More work per combustion can be done a few different ways. The lazy way is displacement. If you make a giant 10-cylinder 8-liter engine, you don't need to do any actual engineering to make power because you're pulling in so much air and fuel. You could also use a smaller engine with a turbocharger to shove more air in there. Or you could do it the hard way: engineering. Motorcycles do it the hard way. Early piston engines were pretty bad at efficient combustion. The airflow had a tortuous path to get from the carburetor to the combustion chamber and again to get back out the exhaust. It took a while for engine designers to realize that air has mass and therefore momentum and would really prefer to travel in a straight line. Car engines do this these days, but motorcycles are really good at it. You can see this progression in engine design over the years. Motorcycle engine designers also realized a long time ago that you can fit 4 circles inside a circle better than you can fit 2. 4 valves gives more area and more airflow than 2. A lot of modern car engines do this, but this has been common on motorcycles for a long time. There is another advantage of 4 valves that I'll get into in a minute, but this better airflow path and increased airflow is part of what makes motorcycle engines more power dense. But they also get to use this airflow better than cars do because they get to cheat a little bit. Motorcycle engines are not playing by the same rules. Motorcycles, and therefore motorcycle engines, are subject to less stringent emissions requirements than cars. They're allowed to emit more pollutants, they are tested at lower speeds, and they only have to prove that they can meet the lower limits for 18,500 miles, whereas cars have to do it for 150,000 miles. Even with the lower requirements, they still have lower carbon dioxide emissions than a car, but they do emit more smog-forming nitrogen oxides. I'll leave the arguing about whether this is a good or a bad thing to people in the comments, but the result is that a motorcycle engine can get more power out of each combustion cycle. A perfectly efficient ideal combustion will only produce carbon dioxide and water, but a real-world combustion will have unused oxygen, fuel, and other components that mix together to create oxides of nitrogen, hydrocarbons, and other bad things. In an ideal scenario, a piston engine would exhaust all of its gases at the end of its exhaust stroke and intake all new fresh air during the intake stroke, but this never happens. A high-power engine will err on the side of completely filling the cylinder with fresh air and a little extra fuel to maximize combustion pressure, ejecting some unburnt fuel and oxygen out the hot exhaust, which will mix together into all those bad things we talked about earlier. A low-emission engine will try for complete combustion and extracting as much power from as little fuel as possible, which just ends up giving less power per combustion. So if you have less stringent emissions requirements, you can make more power. But this is not the only reason that motorcycles make more power. The real cheat code here is revs. To get a car engine that revs past 11,000 RPM, you need about $3 million. But you can buy a Kawasaki Ninja 500 that spins to 13,000 RPM. In fact, for that same $3 million, you can buy 500 Kawasaki Ninja 500s. Motorcycle engines spin fast, and they do this by virtue of being small, or more specifically, being lightweight. You may know that an object in motion tends to stay in motion, and objects inside a motorcycle engine tend to change directions repeatedly many times a second. The heavier something is, the more it resists changing direction, and the faster you spin an engine, the more force it takes to change the direction of the piston and the connecting rod. And at some point, the force will be enough to tear the piston and connecting rod apart. You can do three things to prevent this. One is making the components stronger, and motorcycle engines do this well. Pistons and connecting rods are often forged and made from high-strength alloys. You can also lower the stress on the piston by lowering the maximum piston speed. A typical car engine will have a bore and stroke that are about the same size, but a motorcycle will usually have a bore almost twice as big as the stroke. Even with the same engine size, this shorter stroke engine will be able to spin a lot faster because the stress is lower at any given RPM. This larger bore also allows for larger valves, which allows for more airflow. But a longer stroke engine will usually have lower emissions because you can get a more complete combustion. So with the lower emissions requirements of a motorcycle, they can take advantage of the higher revs you get with a shorter stroke. The last thing you can do is make things smaller. Smaller is lighter, and lighter spins faster, but smaller is also less powerful because you have less fuel and air doing combustion work. So instead, you make everything smaller, and then you make 4 of everything. Making the piston and connecting rod light and strong is an engineering challenge, but doing it with a Valvetrain is much more difficult. To let fresh air into the engine, a camshaft pushes down on a poppet valve, and this is where the problems begin. You can accelerate a valve open pretty quickly, but valves have mass and therefore momentum. Valves rely on springs to close them, but if you open too quickly, it can ramp off the camshaft and float. Contrary to popular belief, float is not so bad on its own. But if the valve ramps too far, it could come slamming back down, which creates a lot of impact load and could break your valve. The valve could also float too long and impact the piston. You can fix this with a stronger spring, but then you need a stronger valve and a stronger retainer, and everything is now heavier and has more momentum, and you've made everything so much worse. The only way to fix this is to make everything lighter. The first thing to do is what we've already done with the pistons. Instead of 1 intake valve per cylinder, you use 2. Now they're both lighter and can spin faster. You can do 3 intake valves, but this leads to diminishing returns and adds cost and complexity. Another thing you can do is use lightweight materials. I used to work for a company that makes valves and Valvetrain components for racing and high-performance engines. We had some car customers like the Corvette Z06, but most of the business was racing, and a lot of it was motorcycles. This is a Formula 1 exhaust valve. It is made from titanium, has a low friction coating on the stem, and if you buy a modern sport bike or high-performance dirt bike, the valves in it will be very similar to this one and maybe even made by the same company. I have oversimplified this a bit. Camshafts don't usually press down directly on a valve. There's something in the middle. On this Hayabusa engine, that thing is these buckets. Actually, these buckets and the shims that go beneath them. The shims are all slightly different sizes to leave a specific gap between the camshaft and the bucket. This is so that when the engine gets up to temperature, everything has expanded so that there is just barely 0 gap between everything. The buckets, however, are added weight, and added weight means lower revs. A lot of the newer high-performance engines, like the BMW S1000RR, use finger followers. The camshaft presses down on the middle of the finger, and then the tip of the finger pushes down on the shim that is at the top of the valve. This adds another friction surface, but the followers are coated in DLC, or diamond-like carbon, which is very hard and very low friction. The finger followers do move, but really only half of them, and they weigh less than the buckets, so the whole moving mass is less and you can rev higher. These also have the added benefit of allowing for a more aggressive and more complex valve opening. There are other ways to get higher revs out of an engine. Formula 1 ditches the valve spring altogether and uses compressed nitrogen. There are 2 advantages to this. One is that you don't have the mass of the spring, so the whole system is lighter. The other is that the spring rate is exponential. A coil spring gives you more force as you compress it, but an air spring gives you a lot more force near maximum compression. So you get a lot of force closing the valve when you need it and a lot less when you don't. There is a third advantage in that without the spring, you don't have to worry about the resonant frequency of the spring. Everything is a spring, especially springs, and everything has a resonant frequency that it wants to vibrate at. If your valve spring has a resonant frequency that is within your RPM range, then it will see a lot more stress and could fail. One common way around this is to use 2 springs for each valve. They're both lighter and they both have different resonant frequencies outside the RPM range. You don't need a spring or even an air spring to close a valve. You can use another camshaft lobe. This is what Ducati does with the Desmodromic Valvetrain. Desmo does have its drawbacks, as well as the Formula 1 pneumatic valves. With the pneumatic valves, you have to have nitrogen on the car, which is not really practical for road cars. And Ducati's maintenance intervals and maintenance complexity is a lot more than most engines. In fact, Ducati has moved away from it on some of their engines for a lower production and maintenance cost. Another great thing about motorcycle engines is how little they weigh. A 200 horsepower liter bike engine might weigh less than 150 pounds, where a 4-cylinder car engine weighs about 2.5 times that much. Part of this is that the engine displacement is less. A liter bike is 1 liter and a car 4-cylinder will be around twice that. And there is a big advantage there. Just like with the Valvetrain, lightweight begets lightweight. If you can make one component lighter, then everything else has less stress on it and can also be lighter, which further drops the stress and so on. But bike engines are also lighter because of the materials used. Engine case covers have been magnesium for years. Magnesium is a great material. If plastic is not enough, but aluminum is too much, magnesium is your friend. You'll see magnesium on car crossbeams and front-end carriers and sometimes on oil pans, but you see it all over high-performance motorcycle engines. A lot of sport bike engines will use aluminum bolts. I hate these bolts because they're one-time use and easy to strip out, and I'm always taking things apart and putting them back together again, but they do drop a lot of weight, especially on a bike engine that already weighs so little. Also, motorcycle engines are not just engines. They are engines with a clutch and a transmission all in one assembly. They are motorcycle powertrains. I love motorcycle transmissions because they are so simple. There are 12 gears on 2 shafts. The power comes in through the main shaft from the engine through the clutch. The clutch works just like a car clutch, except they have a dozen or so friction plates sandwiched between steel plates rather than one big friction plate. The outer part of the clutch, or the basket, always rotates with the crankshaft, just in the opposite direction. The friction plates rotate with the basket, connected with the tabs on the outside. The steel plates engage with the clutch hub, which is connected to the main shaft. There are 6 gears on the main shaft, with first gear being the smallest and 6th being the biggest. There are 6 gears on the counter shaft or output shaft, with first being the biggest and 6th being the smallest. A motorcycle transmission is a constant mesh transmission, so the gears are always engaged with each other. First gear input is always engaged with first gear output, and so on. This works because only 4 of the gears on the input shaft rotate with the shaft, and 2 of the gears on the output shaft rotate with that shaft. All of the rest of the gears are freewheeling. The gears that rotate with the shaft do so because they are connected with splines. So when you're in neutral, the fixed gears on the input shaft are only meshed with the freewheeling gears on the output shaft and vice versa. The way you transmit power is by connecting one of the freewheeling gears to one of the splined gears. And you do this by sliding the splined gear over so that the lugs on the side engage with the holes on the freewheeling gear. Then you have a path from the main shaft to the output shaft. I love the simplicity of this. There are no synchros, no belts, no solenoids, nothing complex, just straight cut gears engaged with straight cut gears. It's lightweight, it's simple, it's fantastic. The way you slide the splined gears onto the freewheeling gears is with a fork, and the way you move the fork from side to side is with a shift barrel. The shift barrel has these tracks cut into it, and rotating the shift barrel causes the forks to move the splined gears so they are either engaged with the gear on the left or the gear on the right, or in the middle, not connected to either. So by designing the tracks in the rotating barrel, you can engage any set of gears you want, usually just one at a time, otherwise the transmission would explode. You probably don't want the barrel in the middle ground either. You want it exactly in the right place, and to accomplish that, there is a star-shaped thing on the end of the barrel with a spring-loaded roller. This roller pushes down into these valleys. You probably noticed there is an extra valley here. That's neutral. That's why it's always a little harder to get a motorcycle transmission in neutral than any of the other gears, because you have to give it a little half push. The barrel rotates with this little grabber that is attached to the shift lever that you move with your feet. If you've tried to shift a motorcycle while it's stopped and it won't go into gear, that's because the dogs on the sliding gear weren't lined up with the cogs on the gear it is sliding into. So you have to roll the bike back a little bit to get it into gear. Some modern cars do have high revving engines with finger followers and lightweight components, but motorcycles have this stuff everywhere and for way less money. There are places where you can improve both power and fuel efficiency, like lighter components, lower friction coatings, and more efficient combustion. And you do see these things creeping into cars, but there's still good reasons why you can't buy a 14,000 RPM Honda Civic making 200 horsepower per liter. Remember when I said that cars were required to prove that they can pass emissions for 150,000 miles, but bikes only have to do it for 18,500 miles? Well, that's because bikes are not intended or designed to go 150,000 miles. Cars are engineered to last 150 or 200,000 miles, but bikes, especially high-performance sport bikes, are designed to maybe 30 or 40,000 miles. Every added mile adds cost. More miles is more fatigue cycles, which means more mass, more metal, better wear coatings. More mass is heavier components, which adds more stress and lowers maximum RPM. Cars also need more power than motorcycles because they're bigger. They're heavier, so they need more power to accelerate because of physics. And the aerodynamic drag is more because cars are cutting a car-sized hole through the air. Cars will generally have a better drag coefficient, but the total drag is more because they're so much bigger. The average new car has about 200 horsepower, and you can get motorcycle engines with more power than this. But they do it at higher RPM, and while driving around at 12,000 RPM is one of the most fun things about a motorcycle-powered car, the fun does wear out pretty quickly, and most people would rather cruise quietly along at 1,500 RPM. So you kind of need bigger engines to get good power lower in the RPM range. You could get the best of both worlds with 2 motorcycle engines, and there are companies that do this for race cars. My friend Robin Shute is building a race car with a Prototipo V8 that uses heads from a BMW S1000RR motorcycle. There's also the added cost. A motorcycle engine might be relatively inexpensive, but a 2-liter V8 has twice as many parts as a 1-liter 4-cylinder, so you're basically doubling the cost. Plus, the transmission is going to see twice the power and a lot more weight of a car, so the gears get heavier, the clutch gets bigger, and you've lost all the advantages of a small, lightweight, integrated gearbox. So, I get it. There are good reasons why car engines are heavier, less power dense, and less cool than motorcycle engines. I want to say that it's an absolute crime that Honda doesn't leverage its motorcycle engine expertise to designing a new S2000 that has a 2-liter V8 based on the CBR engine. But it would be a whole new engine program because, as I said before, motorcycle engines are playing to a very different set of rules for emissions and longevity. A 14,000 RPM S2000 would be amazing, but they're not going to do that because it wouldn't pass emissions, and even if it did, they wouldn't sell a car with an engine that is only designed to last 40,000 miles. Motorcycle-powered cars are better, but only if they're lightweight, and nobody makes one from the factory, which is fine. I'll just have to keep doing it myself.
You may have noticed a new workbench in my office for this video. I did all the disassembly of this motorcycle engine on my new Flexispot E7 Plus Max standing desk. I have a different standing desk for my computer and I kind of hate it. It's not very stable, it doesn't hold very much weight, and it feels like a mild California earthquake would put all the contents on the ground. So when I decided I wanted a new workbench for my office, I looked for something better, something with 4 legs, each with its own motor, something that could easily support a motorcycle engine and a slightly overweight YouTuber, and maybe a couple of curious kittens. This is a standing desk, but it is easily robust enough to be a real workbench. That's why I got it, so I can rebuild this motorcycle engine adjusted to a comfortable height without having to worry about it collapsing. The desk has a static capacity of 660 pounds, so I could have 3 of these engines on here and still have capacity left over. The 3-stage legs adjust to a wide range of heights, the lowest sitting height to the highest standing height, and of course the perfect height to work on it while standing or sitting, and also the perfect height to, say, easily transfer a motorcycle engine from a different table. Not exactly the typical use case, but if it's good enough for what I'm doing with it, it's good enough for just about anything. It comes with magnetic cable organization, a memory keypad with a USB charger, and a 15-year warranty. I've used a motorized sit-stand desk for a while, and it is nice, but with a flimsy, cheap desk, the disadvantages start to outweigh the advantages. Check out the E7 Plus Max desk on Flexispot's website. Also, check out the E7 Plus if you're on a tighter budget. Both desks are stable, capable, and can be ordered with a variety of durable, beautiful tops. And of course, it's Black Friday time, so there are great deals. Shop now and mention Superfast Matt at checkout and use my code to get an extra $50 off your E7 Plus Max standing desk. Click the link in the description to learn more.